Hello and thank you for watching this technical presentation. Today we will share an application report on a new accelerator Lipoment FC210 and its performance in cement-bonded refractory Castables. The goal is to compare FC210 with 3 common Li-used accelerator routes and to validate not only how fast but also how controllable and robust, especially under low temperature installation conditions. On this page, we define the comparison framework. We benchmark FC210 against 3 common accelerator technologies: lithium salt sodium aluminate Na-Lo2 and CAD20. We evaluate to target systems: a silica fume-free ULC system and a high silica LCC system. The evaluation chain is fixed and data-driven. Calorimetry first, then setting time and flow, then early and dried strength, and finally post-firing properties. Under these test conditions, all conclusions are tied to the original tables and figures used in the report. This report follows a 5-stage validation logic from a 2E. Stage A is matrix I calorimetry, used to establish an intrinsic acceleration fingerprint in a silica fume-free environment. Stage B is matrix to calorimetry, which stress tests robustness in a high silica environment with dispersant. Stage C is a dose response study to define an operational low dosage window, staged and stage year full application trials at 10 degrees Celsius, first in ULC then in high silica LCC, to close the loop from mechanism to engineering performance. Matrix I is designed to isolate intrinsic acceleration behavior by eliminating high silica interference. The system uses alumina and Ca71 cement with a fixed dispersant, and the accelerator is the only variable. The objective is to compare fundamental acceleration potential across contenders. We focus on peak position, time to peak height, and peak shape in isothermal calorimetry at 20 degrees Celsius. Under these test conditions, this matrix sets the baseline for interpreting later setting window and strength acceptance results. Here are the matrix I calorimetry curves. Under these test conditions, FC210 and lithium salt show early, sharp concentrated main peaks, indicating strong intrinsic acceleration. CAD20 advances the peak moderately but remains later. Then FC210 and lithium salt Na-Lo2 shows the latest and weakest peak, indicating the lowest intrinsic acceleration in this system. The qualitative ranking, based on peak timing and intensity, is lithium salt approximately equals FC210, both stronger than CAD20, and Na-Lo2 is the weakest. This page translates peak behavior into engineering meaning. In general, an earlier and more concentrated peak corresponds to a shorter induction period, faster setting, and quicker early structure development. However, under these test conditions, calorimetry alone is not enough to confirm field usability. A very strong acceleration pathway can also compress the working window and create control risks. The key engineering question becomes, can we achieve acceleration with a controllable window? That is why the next step is a robust nest test in a high silica environment. Matrix 2 introduces a high silica and dispersant environment to test chemical robustness. We add reactive silica and use STPP as the dispersant, which better simulates a practical LCC chemical environment. Many acceleration routes can look strong in a clean system but become passivated or destabilized in silica-rich systems. Under these test conditions, Matrix 2 is designed to expose interference, resistance, and to detect whether an accelerator keeps its effect, weakens, or even reverses direction. These are the matrix to calorimetry curves. Under these test conditions, the lithium salt curve nearly overlaps with the blank, meaning its heat flow signal is essentially neutralized. In contrast, FC210 still shows a distinct and early exothermic peak, demonstrating robust performance maintained in the high silica environment. NaL02 and CAD20 show some acceleration, but their peaks are visibly weaker or less advanced than FC210. This page clearly separates robust from neutralized behavior. This page explains the most critical risk in high silica systems. Performance reversal. Under these test conditions, if an accelerator's mechanism is passivated by side reactions with reactive silica or dispersant chemistry, the practical outcome may not be just slower, it can manifest as significant retardation of setting in the final castable. That is an engineering red line, because it causes process instability and loss of controllability. The next steps, therefore, quantify dose efficiency and validate full-scale performance in both ALK and high silica LCC at 10 degrees Celsius. Now we move to the dose-response design to compare efficiency per unit dosage. Under these test conditions, we study CAD20, FC210, and NaL02 across 4 dosage levels: 0.2%, 0.4%, 0.6%, and 0.8%, using matrix equilibrium try at 20 degrees Celsius. Lithium salt is excluded from this stage because its operational window is extremely narrow and high risk, as indicated by its flash setting tendency in applications. The output goal is a data-driven, low-dosage window strategy that balances performance with control and reproducibility. This page compares how quickly each accelerator responds as dosage increases. Under these test conditions, FC210 shows the steepest response slope and achieves significant acceleration, even at the lowest dosage range, around 0.2 to 0.4. CAD20 shows a moderate response. Its effect increases steadily but remains less efficient than FC210 at equivalent levels. NaL02 has the flat test slope, requiring higher dosages to reach a comparable shift. A key boundary note: precise numerical values of peak shift versus dosage were not provided in the source report, so this is a qualitative curve-based comparison. This page turns the curves into an adoption strategy. Under these test conditions, an effective strategy must hit the final setting target while maintaining a practical flow window, and it must avoid flash set and performance volatility to ensure reproducible field results. High-efficiency pathways like FC210 can reach target performance at lower dosage, which reduces cost and potential side effects. Low-efficiency pathways, like NaL02 in this comparison, often push toward higher dosage with diminishing returns and higher risk of system instability. The next step is to validate the full setting and strength chain in a 10 degrees Celsius ULC application test. Now we enter the 10 degrees Celsius ULCC application test. Under these test conditions, the ULCC formulation is a high-purity, corundum-based system. We evaluate a full set of engineering acceptance criteria: initial flow, final setting time 24 hour more, 110 degrees Celsius dried cold crushing strength, and post-firing properties at 1500 degrees Celsius. The purpose is to translate intrinsic acceleration potential into practical performance while identifying operational risk boundaries. This page shows flow and final setting time in ULCC at 10 degrees Celsius. Under these test conditions, the blank control has a final set time of about 480 minutes. FC210 at 1% reduces final set time to 45 minutes, with negligible impact on initial flow, essentially maintaining workability. Lithium salt at 0.1 causes flash set in less than 1 minute, making the material unusable. NaL02 at 0.1% reduces final set to 400 minutes, and importantly, a lower dosage of 0.03 causes significant retardation, with final set around 460 minutes. CAD20 at 1% achieves a 60-minute final set, but with a tangible loss in initial flow. This page summarizes ULC performance as a decision-maker view. Under these test conditions, ULC success is not just faster, it requires a controllable window, and both flash set and unpredictable retardation are engineering red lines. The workability map plots setting time versus flow retention. FC210 sits in the preferred quadrant. Short setting time and sufficient flow retention. Lithium salt falls into the flash set region, representing a critical process and safety risk. CAD20 is viable but compromised by flow loss. NALO2 is positioned as unreliable, showing insufficient acceleration at higher dosage and retardation at lower dosage. Now we look at the strength chain in ULCC. Under these test conditions, the 24-hour Mo increases from 0.85 megapascals for the blank to 4.05 megapascals for FC210, which is about a 376 increase. CAD20 reaches 3.05 megapascals, and NALO2 reaches 3.15 megapascals for 110 degrees Celsius dried cold crushing strength. The blank is 113.5 megapascals, while FC210 reaches 125.9 megapascals, about a 10.9 increase. Lithium salt is not comparable here due to flash set, which eliminates a usable working window. This page checks whether acceleration creates a post-firing penalty. Under these test conditions, at 1500 degrees Celsius, the blank control shows a cold crushing strength of 240.8 megapascals. FC210 at 0.1% achieves 236.5 megapascals, nearly identical to the blank, indicating high temperature strength. Retention remains in a reasonable and desirable range. CAD20 and NALO2 both show an disable decrease to around 222 megapascals, approximately 7% to 8% lower than the control. This supports that FC210's acceleration mechanism does not introduce detrimental phases that reduce high temperature structural integrity. This page closes the ULCC loop. Under these test conditions, the evidence chain is coherent. Calorimetry explains intrinsic potency. The setting window confirms field usability. Strength results prove engineering value, and post-firing data checks long-term integrity. FC210 forms a closed loop with correct direction, controllable window, strong early strength gain, and stable post-firing retention. It also illustrates an important boundary. Potent does not always mean usable. Lithium salt can be potent in calorimetry, but flash setting makes it unusable in practice. Next, we move to high silica LCC to validate robustness and direction risk. This section validates performance in a complex, silica-rich LCC system at 10 degrees Celsius. The objective is to evaluate accelerator behavior in a bauxite-based LCC containing a high level of silica fume, a known challenge environment. Under these test conditions, we ask two questions. Does the accelerator maintain effectiveness in the presence of reactive silica and chemical dispersants? And is there any risk of effect reversal that would cause retardation instead of acceleration? We evaluate flow, initial and final setting time, 24-hour MOR, 110 degrees Celsius dried CCS, and 1000 degrees Celsius post-firing CCS. This page shows the most critical result in high silica LCC, the direction of final setting time. Under these test conditions at 0.1% dosage, FC210 reduces final set time from 300 minutes to 100 minutes, a 67% reduction. CAD20 and NALO2 are also effective, bringing final set time to roughly 120 to 130 minutes. In stark contrast, lithium salt fails completely, extending final set time to 480 minutes, which is significant retardation and a critical process failure. For workability, the initial flow stays within an acceptable band, but CAD20 shows the largest flow loss. FC210 and NAL02 show moderate flow loss, while lithium salt shows flow loss as well, but its main failure mode is significant retardation. This page explains why the high silica outcome is predictable from Matrix 2 and how to adopt safely. Under these test conditions, lithium salt's failure was warned by its flat heat flow curve in Matrix 2, indicating its mechanism was neutralized. That neutralization manifests in the full LCC formulation as significant retardation. With a 480-minute final set, FC210 shows the strongest heat flow signal in Matrix 2 and successfully delivers a 100-minute final set in LCC, confirming chemical robustness. For adoption, a low-dosage entry point is recommended. FC210 at 0.05 halves final set, time from 300 to 150 minutes, more than doubles 24-hour strength, and slightly increases flow by about 2%, preserving workability. Now we compare early and dried strength gains in high silica LCC. Under these test conditions, FC210 delivers the highest early and dried strength. The 24-hour MO increases from 160 megapascals for the blank to 4.38 megapascals for FC210, a 174% increase. CAD20 reaches 4.01 megapascals, and NAL02 reaches 4.02 megapascals, both around 151% increase. Lithium salt reaches only 210 megapascals, a 31% increase. For 110 degrees Celsius dried CCS, the blank is 67.63 megapascals, and FC210 reaches 104.16 megapascals, a 54% increase. CAD20 and NAL02 are around 100.7 megapascals, while lithium salt is only 70.22 megapascals. With the previous lie identified, significant retardation risk. This page verifies whether the advantage extends to post-firing strength at 1000 degrees Celsius. Under these test conditions, FC210 achieves the highest post-firing CCS at 115.4 megapascals. NAL02 and CAD20 also show good retention, reaching around 113 to 114 megapascals. The blank is 105.8 megapascals, and lithium salt is 103.2 megapascals. This completes the performance picture in the high silica LCC system, confirming that FC210 provides best-in-class performance from setting control through early strength and into high temperature strength retention. This page provides a structured comparison across key dimensions. Under these test conditions, FC210 is the comprehensively superior and most balanced option. It delivers controlled acceleration with a 100-minute final set, the highest 24-hour MOR gain at 174%, the highest 110 degrees Celsius CCS gain at 54%, and the best post-firing retention at about 115 megapascals. It also supports a wide controllable dosage window and shows strong robustness proof in Matrix 2. CAD20 and NAL02 show effective acceleration and strength, but each compromises flow retention and has narrower operational boundaries. Lithium salt is not recommended. It shows flash set in ULCC, significant retardation in LCC, and no signal in Matrix 2, indicating poor robustness. This is the final quantitative and semi-quantitative summary. Under these test conditions, the KPS core board confirms FC210E's advantage in both systems. In ULCC, FC210 shortens final set time by 90.6%, increases 24-hour MOR by 376%, increases 110 degrees Celsius CCS by 10.9%, and keeps workability neutral at about plus 0.6. In high silica LCC, FC210 shortens final set time by 66.7%, increases 24-hour MOR by 174%, increases 110 degrees Celsius CCS by 54.0%, and keeps workability manageable at about minus 5.2%. The radar chart shows the same message. FC210 is balanced across acceleration efficiency, high silica robustness flow retention, controllability, and post-firing retention. CAD20 and NALO2 are strong but less balanced, and lithium salt critically fails on robustness and controllability. Thank you for your time. If you would like to run joint trials, request samples, or discuss adoption in your specific castable formulation, please contact us.